I'm delighted to welcome Jeff Ovall, who will talk to us about spatial localization of eigenvectors and waves in complex media. Okay.
Well, thank you very much, Alexi, and thank you everybody who's here. I appreciate the opportunity to share this work that I've been working on with my student Robin Reed for the past, I'm guessing 3 years. Time gets a little squishy in the COVID era, so I think it's about 3 years. And if you look down here and see 45 slides, don't be dismayed. I have no intention of really covering all of those, but I have a bunch of slides there ready that if I've said everything that I really want to make sure that I say, and we still have time, I could go a few different directions, depending on your interests. Oops. Here we go. So I'll start with the eigenvalue problems, and I will eventually say something about waves, but the heart of the talk will be about eigenvalues and eigenvectors of differential operators. And I'll pose it in the strong form like this. And for most of the talk, probably for all of the talk, unless we want to try it for little non-self-adjoint operators, it'll be the standard linear elliptic operator, where I've got the diffusion coefficient here, which in 2D, I think I could assume that it was just in L infinity, but in practice, piecewise smooth, symmetric, positive, definite, almost everywhere, usual kinds of things. And C is non-negative and also piecewise smooth in practice. But the typical kinds of assumptions that would allow you to say that you have an orthonormal basis of eigenvectors, you can make it orthonormal, and that the eigenvalues are non-negative and in particular real. It will matter that they're real for some things that I say for this operator. And the assumptions I was just stating about the coefficients A and C imply through unique continuation that no eigenvector could ever vanish identically on an open set. They couldn't do that, but certain properties of the domain, the geometry of the domain, the coefficients of the operator, perhaps the boundary conditions, which for here I'll make this, but that's not truly a restriction, could cause certain eigenvectors to be nearly zero for much of the domain. And we'll see what I mean by localization. On the next several slides, I'll have loads of examples. And I'll start with a simple one in 1D. In fact, a lot of them will be in 1D, and this will be what I call the model problem that I return to illustrate various things about an algorithm that I'll describe later. And just 1D unit interval, negative Laplace plus potential, and the potential is piecewise constant. I split the interval into 4 equal pieces, and I picked 0, 80 squared, 0, 400 squared as the potential. And it's a simple enough problem that if you wanted to check out for a little while, you could probably almost solve this analytically. Because on each subinterval, you know that the solution of the equation has to be either a combination of sines and cosines, if the eigenvalue is larger than the potential, or the hyperbolic sines and cosines if it's smaller than the potential. So you can write down those things and then just continuity equations. The function has to be continuous at all of the junctures between subintervals, and its derivative does. And this could give you, if you fiddle with it, a single nonlinear equation that when you solve it, you determine the eigenvalues, and then you can reconstitute the eigenvectors. I'm just showing the first 16 here, just to see what I mean by localization. We'll quantify that in a bit. But whatever it means, you might say these first 12 eigenvectors are spatially concentrated near the third subinterval or near the first, and they seem to alternate back and forth. And then the behavior begins to change right when the eigenvalue breaches the first, what I'll call the first potential barrier, the 80 squared. As soon as that happens, we're starting to see a different behavior. And for me, because it was a simple enough problem and I could just compute all kinds of things, say the first 500 eigenvalues and vectors, just to get some intuition, I was curious what would happen right around the time I breached that barrier. Are there any surprises? And here's how they look. So here is the last eigenvalue and the eigenvector before I've breached 400 squared and the first one after it. And whatever's happening here, okay, I want to classify it as localization, but it's not like a rapid decay outside here. We just have a rapid oscillation with a small amplitude. And then the story gets a bit more complicated out this way. I just wanted us to see some pictures to kind of get a feeling for this sort of thing. And as I go along, do feel free to interrupt. I don't know what the tradition is, waiting till the end or whatnot, but ask what you like as we go. So I'll make a connection briefly with waves, because this is where a lot of the interesting applications are. So again, well, I guess this could be in any dimension, but a standard wave equation with a particular kind of external stimulation that can be factored in this way, a spatial bit, and then the cosine that oscillates with a frequency that we can pick. An initial position or displacement and velocity. So as we know and probably teach, you can expand the solution in terms of the eigenvectors. And in this particular case, you can write down explicitly what the coefficients are with respect to time. And the only reason I write it out precisely like this is to illustrate, well, a few things, I guess. The coefficients are integrals of the displacement and velocity and this function g against the eigenvectors. And you expect that as you go up higher in the spectrum, these are highly oscillatory. So integrating against a highly oscillatory function should give you numbers that are close to zero. So probably these waves, what you're really going to see in practice spatially is the behavior of the low end of the spectrum, those eigenvectors. With the exception of what happens if you start tickling the system near, near one of these square roots of the eigenvalues, then that could emphasize the behavior. And I'll just illustrate that with some pictures with exactly this model problem that we saw before. And now I just have, for the spatial bit of the external force is just constant 1, so it's really just oscillating in time, the stimulus. And I start at rest, zero boundary conditions. And if I'm tickling the system far away from any of its resonance frequencies, you really just do see basically the profile of the first two eigenvectors that we looked at before. If I start cranking it up a little bit, I start to emphasize the third one a bit more. And then finally, this is pretty close to, its square is pretty close to the smallest eigenvalue. And then we just essentially see this profile. Time is going that direction. But we can crank it up higher and get some other interesting behaviors. And when I finally got up this high, it was emphasizing that for me, what was an unexpected eigenvector, something that was localized high in the spectrum. So I just wanted you to see that because, why might scientists or engineers care about this thing? I care about it for my own reasons. If the problem is challenging, it's got my interest, probably. But it's this idea that if eigenvectors can be localized, then that implies localization of waves, at least at certain frequencies. And I've mentioned a few different application areas, but I'll just emphasize this one with noise mitigation, in particular outdoors. Because if you're indoors, protected from the elements, you can have all kinds of materials that you might imagine that make a good sound buffer. But outdoors, things need to hold up to the weather. And this is an example of a wall with a funny pattern here that was designed by the Colas company, some international organization I had never heard of before that does a lot of building like this. And it was designed such that when cars are driving along here, the types of frequencies that they emit, when they hit the wall, it doesn't bounce back. Those frequencies get stuck at the wall. And I've got just a copy of a patent here, a US patent by a number of people, all of them French here, and they also have a French patent. One of them is Marcel Feloche, who is a really serious analyst. His name will pop up again a couple of times. And these walls apparently work well until they don't. And when they stop working well, is when people start stuffing trash in those holes, or birds, deposit little sticks and things, and it destroys the geometric features, because it's really reliant on that for localization. So the story here of localization, as far back as I can trace it, and this is about as far back as most people trace it, starts with this guy, Philip Anderson. In the late 50s, he was working at Bell Labs. And he's a theoretical physicist, but some of the experimentalists there were doing experiments, and he trusted their results enough to say that that our current models for understanding the way electrons should pass through a lattice cannot accommodate what we're seeing here in these experiments. So he went about trying to come up with the simplest mathematical model he could that could describe it. Diffusion through what he calls random lattices, and he had ideas about just impurities at lattice points that could cause electrons to sort of get stuck in their journey through the lattice. And if I happen to outlive my wife, this piece from his Nobel Prize speech is going to go on my tombstone. One has to resort to the indignity of numerical simulations to settle even the simplest questions about localization. Yeah, it's a nice provocation there. Now, he wrote the paper in 57. It didn't get much traction for the first 10 years or so, but you can get a sense here. I just pulled this off of Web of Science a few days ago, of people are taking notice. They have taken notice. A lot of these papers are on the physics side of things. And there were a couple of retrospectives at the 50-year mark, a 6-page review paper that really hits the physics side of the discussion, an interesting discussion of applications, and then a 600-page book that has at least one mathematician contributing an article. So on the math side of things, I'd say that a lot of understanding has been gained in the past decade or so. And a big push has been done by this first team. I mentioned Feloche earlier. That was one of them on that patent. The rest of these are US, but it's a big team. It's a big team, a few Nobel laureates in physics. This is the one that has the big $10 million grant, so the Goliath. And what I'm doing for each of these is just mentioning the first paper that I've found where they're really picking up this thread. So Proceedings of the National Academy of Science in 2012, where this group here focuses on what's called the landscape function. And I'll highlight what that is a little bit later. And they do some computations, but really the focus is on a theoretical understanding of what's driving localization. And a more recent group, headed by this Stefan Steinerberger, who's at the University of Washington, does something similar, but instead of a landscape function, takes a rough potential and then smooths it in a way. There's a universal kind of smoothing that he can prove can help explain some of the localization. And the last two groups, mine included, are actually really doing computations, like numerical analysis kinds of things, where certain parameters could get you convergence toward the right answer, and trying to analyze stuff like that. Yeah, maybe that's all I'll say, although I want to highlight that it will be clear, at least to one person in the audience, where some of the ideas that I'll introduce are inspired by, inspired by your work, Marco. And we came into it last here. This is our paper is accepted in Mathematics of Computation. I don't know when it will appear. So I'll talk about this landscape function a bit, because it shows up in all of the Feloche and my Baroda papers with their whole team. It seems to appear the same result over and over again. And actually, I'll highlight it at the bottom, that instead of looking at the eigenvalue problem, if you look at this particular source problem where the right-hand side is a 1 and solve that problem, then that function controls all of the eigenvectors point-wise if they're scaled appropriately. So initially you'd scale it to have a unit norm, a unit infinity norm. And then you also scale according to the eigenvector. And it's actually not a hard proof. In fact, there's a more general result that you could prove. If you're in a situation where you have a maximum principle, like a weak maximum principle, a typical pattern is to use that to prove a stability result. And I've written down a pointwise stability result. And this is maybe an exercise you give students in analysis, something like that, that you can always pointwise control a function by its boundary values in the L infinity norm, how the operator acts on it in the L infinity norm, and this landscape function. And here's a little proof based on the maximum principle, or at least a sketch of it to give you an idea. Yeah. And so the Fallot-Schreiber-Roeder result is just a special case of that. So here is some pictures from their initial paper, where the operator, and this is the operator that they tend to focus on. They keep a simple domain like a square. They break the square up into all kinds of small squares and allow the potential to be essentially random, choosing essentially a random potential there. And the landscape function for that looks like this, all kinds of peaks and valleys. And here's a superposition of the first 5 eigenvectors. And even though on the physics side of things, we would only call the one associated with the smallest eigenvalue a ground state, it's kind of typical in this setting to call all of these things ground states, because they sort of look like a ground state. And each of these peaks corresponds pretty well to the highest peaks that we see over here. Yeah. These next examples will illustrate that easier, with just in 1D. So I did the same sort of thing, that chopped up the unit interval into 32 pieces and let the potential be random, well, whatever the computer attempts at random, between 0 and 100,000. And the landscape function is the one on the top, and there's its negative, and they give a nice envelope to every single eigenvector, provided I scale them the right way. I scale them the right way in this sense. So there's the first one that nestles right nicely in that biggest peak, one that comes up in the second peak, one that comes over in the third peak, and so on. So here's something that's not understood, as far as I know. So a theorem says that all of these eigenvectors, the theorem that I showed, shows that all of these eigenvectors, when you scale them like this, will be between the 2 gray curves. But it does not directly tell you that most of them will focus or be sharply concentrated near one or other of the peaks. That's something that still, I think, is not understood properly. But I'm just showing you the first 20 or so to get a sense here. If I relax how large the potential can be, then the picture is not quite, I mean, you still get the localization, but it's not quite as dramatic as we saw in the previous picture. And the higher up you get in the spectrum, okay, different things happen there. I've got all kinds of pictures. But I'll go back to this model problem to illustrate that even though that theorem is always telling the truth, what it is saying isn't very useful necessarily once you get higher up in the spectrum. So I didn't have to get very high in the spectrum, say 20, before certainly it's the case that all of the scaled eigenvectors is sitting in between the gray curves, but it's not really telling you much. And we had seen earlier that when the eigenvalue breaches this 400 squared barrier, there'd be something localized in this last little bit over here. We wouldn't even see it. It's telling the truth, but it's not that helpful. So, and again, I want to say that if you have questions along the way, please just fire away. We're a small enough group, I think it doesn't have to be moderated in any way. So one of the first things I wanted to do is try to quantify. These are pretty natural quantifications of localization, because I want to be able to say something like, is an eigenvector localized in this region to within this tolerance? I want to be able to just, answer questions like that. So I have here 2 complementary measures of localization. The intuition being that if your function is nearly entirely concentrated in the region R, then this ratio is close to 1, and that ratio is close to 0. It's just that idea. And they're complementary in the sense that if you square them and add them up, you get 1. And because they're ratios of norms, they're scale invariant, which is a good property because so are eigenvectors. Scale them how you like. So here was what, when I wanted to boil down something, a problem, boil it down to a level that I could present it to my student and we could work on something clear together, this is what we came up with. That if someone gave us a subdomain and a tolerance, probably a small one, some large interval where we're hunting for eigenvalues of the operator, we wanted to be able to find all of the eigenpairs of the operator where the eigenvalue was in the energy interval or frequency interval, whatever we want to call it, that was prescribed, and that the concentration, that it was concentrated or localized within that region to the tolerance, something like that. That's kind of a key task. We might be interested in, later on in broader things, but if we can do this, then we could build up to more complex things. And okay, this is assuming I'm given a region. Well, one way I could find those regions potentially is to use the landscape function and use that to give me ideas about where I might expect things to localize. And the reason I highlighted this part in red is that if you were to think about all the eigenvalue solvers that you know, they're designed to find eigenvalues that are in a specified interval or maybe a specified region of the complex plane. That's what they're designed to do. They're not designed to handle this sort of constraint. So it's just a different sort of thing. And what I don't want to do is be completely inelegant in my approach and just find every eigenpair where the eigenvalue is in here and then go through afterward and toss out all the ones that don't satisfy the condition. I like to have something more elegant that tries to address both of these concerns at once. So I put large in bold here. Could I modify the problem so that both constraints, this one, and I'll call that geometric kind of constraint, that both constraints are encoded in the eigenvalues of a new problem, so that I could just reuse eigenvalue solvers that currently exist. And then how would I decode afterward and get the information I really wanted about the original operator? So that's the strategy here. And here's where we'll see some pretty obvious motivation from Marco's work. So at least I'll give heuristic motivation, intuition here, and then some theorems and all kinds of empirical evidence afterward. If you had an eigenpair of the original self-adjoint operator, and it was really concentrated in the region R, so this delta measure is small, the tau measure is near 1, the delta measure is small. Well, if you took it to the extreme and just pretended that the function actually identically vanished outside of the region, then applying that same eigenvector to this shifted operator, complex shifted operator, and that's the characteristic function of the region I care about, would just take the eigenvalue and push it straight up, all the way up here. Now, that's not really what's happening. We know these things can't vanish identically on any open set, but the intuition says there ought to be an eigenpair of this new operator where the eigenvalue is close to lambda plus is, somehow close to it. So just restating the original problem, which was finding real eigenpairs of the self-adjoint operator, where the eigenvalue is in an interval and it's the eigenvector is concentrated in the region to a tolerance. The new problem is to just look at the eigenvectors of this shifted operator, complex shifted operator, where the eigenvalues, this is my hunting ground now. If in the ideal sense, you would take anything from A to B and you push it straight up to this interval from A plus is to B plus is. But we have this shifting parameter that we pick, some positive number. And we've got this tolerance, delta star, there it is. And that gives a radius. So our hunting ground is this region here, the lower half of a hockey rink, where everything is within S delta of the line segment A plus IS to B plus IS. But that's where we should hunt for things. If there was something localized for L, then we will see it. We will see an echo of it in the eigenvalues of LS, and we'll see that echo right up here. So that's the statement. Now, originally, when I'd submitted this paper, and it was even accepted with this error, I caught it later, the words sufficiently small were absent from the theorem, because I had assumed and thought it was obvious that the operator LS was a normal operator, but it is not. Once I tried to explain it to someone, I realized it was kind of obvious that it wasn't. But that escaped me for quite a while. But here's the statement. If you have an eigenpair of L, regardless of whether or not the eigenvector is localized in a region or not, just some eigenpair, and S is sufficiently small, whatever that means. And it's red right now because I'm not quite satisfied with my answer about sufficiently small, what that means. But there will be an eigenpair of the shifted operator where the eigenvalue is close, within that hockey rink shape that I mentioned, close to lambda plus IS. And in fact, if I looked at the difference between these things and divided by IS and let S go to 0, it would be this concentration measure. It would be precisely this number. That's what it would go to. And here's a sketch of the proof. This kind of perturbation of the original operator is holomorphic in S. And it's of a really nice type that Kato mentions. I can't remember his exact classification, but all of these operators LS have precisely the same domain as L, as L does. And because it's such a nice perturbation, we can identify a sequence or a parameterized sequence of eigenvalues and eigenvectors that converge to the eigenvalues and eigenvectors that we want. In fact, even converging with the right multiplicities, you have different sequences doing this. And then it's just a bit of algebra. And you'll have access to these slides. And I can send them to you directly if you like. It's a big file because there's a lot of pictures. But a question for me is how small is sufficiently small? My theorem has this in there and I don't know. I don't know yet. So what I've done is I've taken my model problem again and I picked some subinterval where I knew there was localization for certain eigenvectors and not for other ones. And I'm looking at the first 17 or 20 of these things. That's probably 17. And the ones highlighted in blue are the ones that are localized pretty strongly in this region. In fact, I'm giving the localization measures in terms of the tau. The ones that are close to 1 are pretty strongly localized there. The really small numbers are localized somewhere else, the other subinterval. And then there are these ones near the end that aren't really localized anywhere to speak of, at least not in a small region. And I'm just testing whether or not this is true, because I can compute all of those quantities. And when S is 1, everything is true. And the statement's always true, localized or not. When S gets to be 100, well, the ones that are in blue remain true. The ones that were really localized elsewhere say false. Okay, fine. And then these ones that weren't very localized anywhere, they're also true, at least for now. But if I push a bit harder, some of those flip to false. So, okay, this is one thing that I'm showing you, but based on my experience, my guess is that sufficiently small has to do with how localized the thing was to begin with. And if it was really highly localized, I can push really hard on it, and it will still satisfy this condition. So those are numbers, and good, because you can, numbers are harder to hide behind, but you can hide behind graphs. You can always make a graph look favorable, or often. So here's a different look at it. What I've done here is I'm looking at the no shift case, the original operator. So the eigenvalues aren't complex, but I can plot the eigenvalue and its tau measure, that particular concentration measure. For the first 17, I've done that. And we see the 6 of them that are really localized in the interval I care about, the 6 that are localized somewhere else, and then these other ones. And now when I take s equals 1, now I'm looking at the real and imaginary parts of the eigenvalue. And if you didn't look very closely at the axes, for example, you'd think they were the same picture. Yeah, it really is capturing the right features here, that the real part is encoding the lambda, the imaginary part really is encoding this concentration measure quite well. I push a bit harder, the picture looks pretty similar. I mean, although you can start to see that there are some differences, and there is some drift in the real part as well. If I push even harder, then one of these things that wasn't localized got excited enough that it became localized. So this is something that is warning me that if I push too hard in the imaginary direction, I can introduce things that I later have to throw away. Because what I'm hoping for is just to highlight all potential candidates that were localized in the original operator just by looking at eigenvalues of the shifted operator. So here is a theorem that will allow us to go back. If we start with eigenpairs of the shifted operator, how should we go back to eigenpairs of the original operator? And the same, I'm looking at localization measures, but I'm looking at them now for the function I have in hand, this complex eigenvector. One thing that you could do or see fairly quickly just by looking at the Rayleigh quotient, the Rayleigh quotient that gives you the eigenvalue in terms of the eigenvector, you can see that the imaginary part of the eigenvalue is telling you directly how concentrated that function is in the region you care about, because you know S, and so you can read off the other thing. But the statement is that there's no assumption about the size of F or S, how hard you push. There's no assumption there. But it says that there will be an eigenpair of the original operator where the eigenvalue is not so far from the real part of your complex eigenvalue. It's close to the real part. And how close? Well, this close, this close. These things that you actually have at hand if you have computed mu. You can get the tau directly from it. You know what the S is. And if you know what tau is, you know what delta is, because they're directly related to each other. And furthermore, we have this residual estimate here. In fact, it's not even an estimate. It's one of these rare occasions where I don't have to write an inequality. It's an identity. That if you just took the real part of both of these things, the real part of the eigenvalue, the real part of the eigenvector, and look at this residual, which is a sort of measure of how far those real parts are away from being an eigenpair of L, you can write down an identity, like so. And this is algebra here, but for sake of time, and because you can have the slides if you want, I won't talk about it. But it is just a few identity, just a little bit of algebraic manipulation and some norms, and I guess the Pythagorean theorem. But looking at this, S is something that we control. And then the delta and the tau, okay, those are something that we just find once we've computed this. But we also know that if you have an eigenvector, you can scale it how you like. Right? We can scale it how we like. And I mentioned earlier that the delta and tau measures are scale invariant because they involve a ratio of norms. So if I can scale how I like, and kind of renormalize the eigenvector, that maybe what I should do is multiply by a complex number, say of unit modulus, so I don't really change the norm, of unit modulus that minimizes minimizes the one thing that I can actually affect. And that's what I'll say on the next slide here. Oh, no, okay, I'm sorry. I'll skip this. I may come back to it. It's a statement about eigenvector closeness, not just eigenvalue closeness, but how close the eigenvectors are to some invariant subspace. Okay, so this is me recopying that last bit where I was saying that I can rescale how I like. And I might as well keep it, if it was unit length, I'll keep it unit length, or I'll keep it the same length it was. And this is a reminder that those quantities are scale invariant. So I can further normalize by just choosing the best complex number of unit modulus, the one that minimizes this. And with a little bit of algebra, you can rewrite that or recast it as a 2x2 Hermitian eigenvalue problem and solve it by hand. So as long as you know what the original norms were, or yeah, you have the original real and imaginary parts, you can write down what this 2x2 eigenvalue problem is and just solve the thing. And you can get real gains here. So I'll show you on the next slide. So here is an eigenpair that I computed of the operator LS, the complex operator. And the dashed one is the imaginary part, the black part is the real. And this 42.14, whatever that number is, oh, by the way, I pushed with 100 here. That's what the push was, push with 100. This number here is precisely what I've highlighted. It's that residual just there. And after renormalization, just multiplying by a different complex number of unit modulus, this is how the function looks, and the residual dropped significantly. Yeah. And that gives me some confidence that if I just rip off the real part here, that's going to be close to an eigenvector of the original operator. And they look like they're pretty close up to sign. Yeah. That was a localized one. I could play the same game with a non-localized thing. And the residual drops, but it's not nearly so significant. And I know it's probably pretty small for you, depending on your screens, but if you just look at the real part of the eigenvalues, you see that there's really strong agreement there. Yeah. So this leads me to an algorithm template, and that's what I want to call it for now, because a lot of different components could plug in to different parts of this template. So here's how I'm envisioning a procedure, and it is partially realized now in code, is that the first thing we do is just look at eigenvalues of this shifted operator that are in a certain region in the complex plane that I showed you a picture of earlier. I go hunting there. And I'll just jump down to the bottom. This is where the bulk of the work happens in the algorithm, and that's by design. If I'm looking for eigenpairs of the original operator that are localized in a certain region, then they will have echoes in this region, and that's my hunting ground. That's where I'm going to be searching for these candidates. And there are a lot of contour integral-based methods. I can, if we have time and if there's interest, I can talk about what we actually use in practice. But these are designed to highlight just the eigenvalues in some region of the complex plane. You just draw your contour and say, give me everything that's in here. And I don't care if there are repeats. I want to get them up to multiplicity as well. And they work quite well for self-adjoint operators and for normal operators, and then maybe for, you can get some nasty operators for which you can break them if they have a Jordan chain or something. So we find all of those things, and this is what I'll call the first filter. And what I'm hoping, and what we observe, is that, say, if there were 300 eigenvalues of the original operator in AB, and say only 8 of them were localized in the region I care about, what I'd like out of this first filter is just to get a list of 8 or 10 candidates. I want it to cut out all the rest of it. So there's no chance that these could have been localized. But for each of them that we do find in this first process, I normalize, just like I talked about before, just renormalize, multiply by a unit modulus complex number, rip off the real and imaginary parts of both the eigenvalue and the eigenvector. And that already may be such a great guess at an eigenpair for the original operator that I stop. But even if it's not, I have an identity which gives me a sense of a residual. I mean, there's a measure there. And at worst, I might do something cheap, a little cheap post-processing to go from that to an eigenpair, maybe a couple of steps of an inverse iteration, just to drive it even closer. I've got a good guess and I can get it even better, faster. And then after I've done that, a final kind of check that maybe this region here opened up the door a little bit too wide. I got too many candidates and I might have to throw out a few of them at the end. So that's kind of a template there. Yeah, okay. That's what I'll say for now with that. And just to illustrate it on the simple example that we've looked at over and over again, this one that I'm highlighting here. Within the interval, if I took the interval from A to B to be 0 to 220,000, it turns out that there are 130 eigenvalues of the original operator in that interval, but only 5 of those are localized in this particular region with this particular tolerance. If I, loosen the tolerance a bit, I could get that 6th one to pop in there. That 6th one that we'd seen. So the first move, the first filter, is to find the eigenpairs of the shifted operator where the eigenvalues in that region that I've shown you a picture again below. And we know what the A and the B and the S and the delta are. I guess I have 2 different choices of S. Push just a little, push a lot harder. So now, right now, and this is why I say it's an algorithm template, right now, for a simple problem like this, we're doing a by-hand matching of these things, looking at the real parts of each and matching it with the corresponding eigenpairs of the self-adjoint operator. And then finally, in the second filter, we just drop anything that didn't satisfy the criterion, the localization criterion. And what we found with this example is that the first filter excluded 124 candidates. It gave us 6 candidates. There were really only 5 that pass, but it gave us 6 candidates. When S was 1, it gave us 6. When S was 100, it gave us 6. I don't recall what happened when S is 10,000. It might have given us 8. It gives us more potentially if we push too hard. But of those 6, in each case, we ultimately had to drop 1 more in the second filter, the one I highlighted in red. And it didn't miss the cut by a lot. If you look at a picture, you might actually forgive it and say, well, maybe I'm having a change of heart. Maybe I will accept this one. But at any rate, it gave you a candidate that was close. That's the one that it dropped. Okay. So at this stage, I'm actually doing all right with time. I could go 5 minutes further, but maybe right now, I just want to invite some questions, or maybe you're interested in some particular thing and you'd like me to pursue that path. Is there anything that's come up so far that...
Could you say something about the contour integral approach to finding eigenvalue?
Sure.
Because with my former PhD student, Salma, we tried this, admittedly for a different problem, which had other pathologies. And we were using some software we got from the group in Manchester, who are kind of the leaders in this. And it worked, but goodness, it was expensive, really expensive.
Yeah. Do you remember what that one was called? It wasn't one of these, was it?
It was I can't remember what it was called. It was a package produced, I think, if I remember correctly, by by Françoise Tisseur and one of her collaborators, maybe Stefan Gutel.
Okay. Yeah. I'm wondering then, I know Stefan Gutel has done quite a bit with this feast.
Okay.
Yeah. And when you see that there, it screams that it must be an acronym. Well, it turns out it's a failed acronym. That doesn't stand for anything. I eventually tracked down the guy because people had asked me, what does this mean? This is the one that we use, feast, and I'll describe it. But a lot of these are, okay, this one I think is the easiest for me to describe because it's a lot like the power method, or the grown-up version of the power method, which is subspace iteration. But it's subspace iteration with a filter, with a filtering idea. So I'll pop to a few slides and just describe what's going on with that. Skip this stuff. Okay, so there's a bit of a history that I just briefly show here. It started with this person, Polizzi, who's a mechanical engineer. And in the paper itself, it's just declared to be feast with no explanation as to why it's called that. And I asked him, and he said it was a failed acronym, that he was trying to torture words to get feast because he decided he really liked that. I mean, fast was an obvious part of it, but what's the E about? eigenvalue, eigenvector. At any rate, he gave up. And so you could read that paper. I think this one is probably a better one to read to understand what's really going on behind it. And this is when Intel, this guy's from Intel, sort of discovered this and realized that it was well suited to the sorts of chips that they were designing. And so now Feast is a major part of their math kernel library for eigenvalue problems. It's really got some nice parallelization features, non-Hermitian problems, all of this for matrices. And then we jumped into the picture, and Stefan Goethel, I guess Stefan Goethel would have been in these ones. His name's not appearing, but he's certainly part of this whole movement here, these ones here, where we thought, okay, you can do that with matrices, and fine. When we discretize the operator, we get a matrix, but could we analyze this on the operator level, just directly? And so that's what these papers are about. Me and one of my colleagues, and okay, you probably know Luca. Marco, you've met Luca, yeah. So here's the idea, is that even though the operator L is an unbounded operator, unbounded differential operator, if you have a function that is continuous on the spectrum and bounded on the spectrum, then this is a result like from functional calculus, that F applied to L is a bounded self-adjoint operator. And if you had an eigenpair of the original operator, then you'll have an eigenpair of the bounded operator that keeps the eigenvector, and that's a key, keeps the eigenvector and just changes the eigenvalue in the way that you would pick if it was your birthday. So how should we choose such a function that highlights eigenvalues that we care about? So one of the ways we do it is you pick a curve, a Jordan curve, a nice smooth closed contour. Often it's a circle, or it could be an ellipse or something. In principle, it could be other things. But you want it to enclose the region you care about, and you want to make sure that that no eigenvalues are sitting on the boundary of your curve. Okay, that's okay. You maybe really can't make sure of that, but you don't want that to happen. So if you could choose that function f in such a way that the mapped eigenvalues in the region you care about are strictly bigger than all the other ones, the ones you didn't care about, that it sort of damps out the ones outside the region you care about, then that's what you want to do. Because we're going to use the power method on this and drive it toward the dominant eigenspace. So a typical choice here would be a rational approximation of the Cauchy integral, which is giving you the characteristic function on the domain. Yeah, that would be the ideal mapping. Annihilate everything outside and keep everything on the inside, map it to the number one. So you can get a rational approximation through quadrature. And the resolvent, so we really on the operator level be integrating the resolvent. Because the resolvent is an analytic function, once you stay away from the spectrum, if the curve you're integrating along is smooth, you can actually get away with using the trapezoid rule, because the trapezoid rule for smooth periodic functions converges exponentially. I mean, it's just rapid convergence for periodic smooth functions. So this is the idea there. So yeah, so if these were your target eigenvalues, then there'd be your target invariant subspace that goes with them. And just like the power method in general, or what do we call it when it's grown up? Subspace iteration, which is really just the power method with multiple vectors. You pick an initial subspace at random. What you'd like to be the case, although it's not so easy to control, is that the spectral projection of your random subspace should be your target invariant space. It should be that, and typically what's done is you have some estimate of the dimension of the space, your target space, and you pick an initial space that's bigger, maybe twice as big initially, and then you'll begin to pare it down over time once you realize how big the space is you're hunting for. And here's subspace iteration on the abstract level. We just take our initial subspace and hit the bounded operator, the filtered version of it, against it over and over and over again. And then one needs to argue that this subspace is driving toward the actual target space. And when you're measuring distances between subspaces, many ways you could do it. My favorite is the subspace gap. So some measure of the distance between these things. You could say it has something to do with subspace angles. But so some of the theorems would be that if you've chosen your filter correctly, which right now is not the contour integral, it's just the rational approximation of it, then this ratio, what's the worst that could happen outside? What's the largest mapped eigenvalue outside? Hopefully that's much smaller than what you're getting on the inside. That ratio there is determining how rapidly you get this decay. And in practice, the filter, you can improve this more and more. So some of the things that could make it bad is that once you draw your contour, if there are eigenvalues of the operator that are just outside, like really close to the contour, that's going to hurt this ratio. But other ways, some ways you could improve it are by really pushing up the number of quadrature nodes so that your rational approximation gets closer and closer to the indicator function. And that could be where some of the expense was that you were seeing, Marco. I don't know what parameters you might have picked.
Yeah, I think we had the problem that it was very difficult to separate the eigenvalues we wanted from other stuff whose location we weren't sure of.
That's right.
And so that our kappa was always close to 1, and then we had to ramp up the discretization, so that was more expense. And then the underlying PDE problem was a truncation of a periodic operator in a semi-infinite domain, so that also brought in another layer of expense.
Sure. Did you follow up with them much? I mean, I know in the meantime, they've been trying to mix and match the nice features of a variety of these integral-based methods.
I haven't followed this up with them. No, I'm kind of waiting for Salma to do some other things first.
Yeah, sure. But yeah, the story of Feast, and I'm sorry if that you already knew all that stuff anyway, but yeah, you drive the subspace gap down, and the distance between the real eigenvalues that you care about and your other set of approximate eigenvalues, and this is a Hausdorff distance between a couple sets of numbers, goes like the square. So this really does behave just like the power method does, but the analysis is just harder, that's all. But the idea behind it is the same. And for me, the region where I know I should be hunting is the lower half of this hockey rink. But it turns out that for the quadratures, even though I know that nothing is above this dashed line, that for the quadratures, it's nice to have it completed. To have it a nice smooth or smoothish domain. And so here's an example of quadrature points, 32 of them in this case. And I want to emphasize that there's a big cost incurred, because every time you do a subspace iteration, you are solving, you're inverting, on the discrete level, you're inverting a linear system for every single one of these points. That's the expensive bit. And then you collect them. And you could do this in parallel if you had those kinds of resources. Solve the systems in parallel independently, and then collect on a single processor the sum involving the quadrature weights. But every time you want to do an iteration, you are solving the same thing over and over. So you probably, it's worth factoring the matrix, because you're going to solve the same system over and over. And if it's nonlinear, then that does complicate things, because now the system does change from iteration to iteration. And there's even more expense. But what I'm showing here is a contour plot of the magnitude of this thing. And what you really want is a rapid decrease, a really rapid decrease away from this red line here is the bottom half of my my hockey rink. So you want things to be near 1 and then drop really rapidly away. That's the sort of feature you want. And okay, some things that could go wrong if you draw a really wonky contour, something that has a nasty aspect ratio, is that the same number of points doesn't work anymore. It's got a really nasty aspect ratio. You have to deal with that. And so this is what I did here. If I had a parameter S, which was 10, and I changed it to 1, what I'm seeing here as nice behavior is gone. It's just gone. But you can ameliorate that by just chopping your region into a bunch of smaller regions of the same type and doing parallel processing, because these are completely independent of each other. If you have the resources, you could pull it off. Okay, that's actually all I had to say about the feast stuff, unless you had more questions about it. I know we're running out of time, but
that's good for me. Thanks.
okay. Yeah. Any other questions, or should I show more pictures? It's always fun to look at pictures. I'll put that there and see if it provokes any questions.
I guess I have a question just building slightly on Marco's question, in fact. So for the operators you're considering, have you got evidence that because computing eigenvalues of non-self-adjoint operators will be more expensive than computing eigenvalues of self-adjoint ones, have you got evidence that going through your procedure will give you like a speed up compared to computing all the eigenvalues of the self-adjoint operator between A and B and then throwing away the ones that aren't localized?
Yes. So yeah, that's what I was saying I didn't want to do. You're right. So what I have seen so far is that even though I'm dealing with this non-self-adjoint operator, it's non-self-adjoint in a very peculiar way, a very specific way that doesn't seem to really slow down the actual solution phase. Like if I was to use feast for both of these things, I haven't observed a significant difference in the timings. So I haven't observed. That's what I can say so far. I think that we would need to, if we really want to sell this, not just based on theory and how the theory might be appealing, but to people that really care about timings, then we have to do the numbers. I haven't written down a bunch of numbers that I can show you. But the observation so far is that the way in which this LS is not self-adjoint isn't hurting us. It's not costly.
Fascinating. Okay.
Yeah. Maybe if I pushed really, really, really hard, it could screw things up, but it hasn't so far. You push the parameter S.
Okay.
Because it's not even normal, right? I mean, I would say, okay, normal is the next best thing, but it's not even normal. And yet it seems to be fine.
It's really interesting.
Yeah.
Thanks.
So I will, the file's pretty big, but so it won't really travel over email well, but I could put a link and then share a link with you if you want to look at the slides. I'll share them.
So perhaps there are more questions for Jeff.
Maybe I'll ask a very basic question. In the very beginning, when you can you repeat how you get the hockey rink shape, sort of the parameter that defines it?
Right. I'll show. Okay, it was. Where do I have these theorems? Okay. So right when I have, yeah, it's based on this result right here. So if I was hunting for eigenpairs of the original operator where the eigenvalue was between A and B, if it was between A and B, then this is now between A plus BS, or A plus IS and B plus IS. And what I'm looking for I'm looking for eigenvalues of this shifted operator that are within S delta of that line segment, with S delta of that line segment. And in fact, there was
the delta is that delta, that ratio.
Yeah, it's that ratio. It's the thing that if something was concentrated in the region R, that delta would be close to 0.
Okay, and that is what defines your hockey rink.
Right. So there is the S and the delta together. The S, the delta, the A, and the B define the hockey rink. And in fact, there's a delta star. I say, here's the tolerance. Your particular delta should be smaller than this. 0.2 was one of the examples that I've given. That gives this kind of radius, and it's everything in the complex plane that is within that distance of the line segment A plus IS to B plus IS.
So
the idea
knowing
that
to look there is not, it's not a trivial thing. That's the result of that theorem. And that is a theorem for which you don't know what small enough is.
That's right.
Okay,
Yep.
got it.
Yeah. So that's one of the reasons why I highlighted that in red, because it bothers me. I mean, okay, in numerical analysis, even Newton's method, you say, if you start sufficiently close to the root, then you're fine. And this is one of those kinds of things, but I'd like to say more, because I have intuition that if you were really dealing with something that was highly localized, that sufficiently small doesn't have to be small at all. This is what I've observed, but I can't prove.
Could I make a remark? I mean, when I was
Sure.
doing work with Salma, one of the so we had to choose, like you, this coupling constant S, and in fact we never chose. I don't think we ever chose S bigger than 2. And one of the problems in our particular case was that if you start to choose S too big, then the real parts also start to go.
Yeah, they move
way away from where you expect to find them. And so then the step of kind of coming back from what you've computed to what you wanted just became for us anyway quite problematic. I think another issue for us was so you're interested in localization arising somehow from either the topology of the domain or from the functions, the coefficients that define the operator. In our case, we were thinking of a problem where the problem was originally singular. We cut it to a regular problem. There'd be some spectral pollution, and the way that we would understand what was spectral pollution and what wasn't was by where the eigenfunctions were localized. And if you've just got one truncation, if you don't have a family, if you've just got one truncation, because you don't want to do a lot because they're really expensive, then there's a real element at the boundaries, a real element of kind of experience of asking, okay, if I've got a function that's concentrated around here, is that a genuine eigenfunction or not? So that was also a source of difficulty for us, and so we could have 2 eigenvalues that were really close together, but one of them had an eigenfunction that somehow was coming from spectral pollution and one didn't, and yet their localizations were sufficiently close because we hadn't chosen a big enough truncation that that the eigenvalues we wanted would be polluted with the ones we didn't want, even despite having this dissipative barrier added in there. And so when you added that to the problem with the contour integral and so on, it just made it really, really tricky.
Right. Yeah. We have, I didn't show those slides here. You can look at them if you like. At least one example that is in spirit kind of like that. Well, not quite. Here, they're both legitimate eigenvalues, but they are extremely close but distinct from each other. And this could come from symmetries in the domain or symmetries in the coefficients. And if you perturb something just a tiny bit, you get localization. Just the tiniest bit, you get localization. But if it's in its standard form, there's no localization. So if you go hunting for it in the way that I am proposing here, you'll introduce false candidates, just perturbing a tiny bit. It wouldn't matter how small S is. You'll see something that wasn't there. So in those cases, unavoidable. But as you say, with experience, you know to expect that can happen and give proper warning.
So are there any more questions for Jeff? Okay, maybe if there's any other questions can postpone for after. So maybe we can give Jeff like a virtual round of applause.
Thank you.
If that's possible.
Yeah.
Okay, thanks. Thank you, Jeff.
I appreciate it. And Alexei, should I make the link available to you for these slides? You share it with whoever you like, whoever
Yeah,
wants.
absolutely. Yeah. You send it to me and I'll send it round.
Right. Well, I'll send you a
That's a good
link because it's a big file. You can just download it. All right.
Absolutely.
Well, thanks so much.
Thank
Thank
you.
you.
That was really interesting. Yes.
Yeah.
Okay, thank you.
Thank you, Jeff.
That's my